So one more time, same circuit, R1, R2. This is a source of confusion for people. This is the direction of the current in that circuit. Okay? If we write Kirchhoff's loop law, you can walk around your circuit whichever way you want. You can start from A, go to B, go to C, then go to D, and then go to E. You could do that. And if you did that, then the difference in potential that you would write will be epsilon for when you walk across the battery, minus I R1 when you go across resistor 1, and minus I R2 when you walk across resistor 2. And when you add those, you should have 0, because you went back to the original point, right? But that's if you walk that way, right? That is the direction of your displacement. What if you went the other way? How does that equation change? And would I get a different answer? Obviously from this equation I can get an answer for the current, for example. If I know the voltage of the battery and I know the resistors, I could solve this equation and get I, right? But what if I walk the other way? Would I get a different answer? Obviously when you walk the other way, the sum of all of the differences in potential should still add up to 0. Because that's just conservation of energy. Shouldn't matter which way you go, right? But now let's do that exercise. Let's walk from A. Instead of going to B, we're going to move in the circuit along this direction, right? So what are the differences in potential that I experience? From A to E, that's 0. From E to D, the current is not going to change direction just because you decide to walk in a different way. The current is still going this way across that resistor. So when you walk from E to D, what happens to your height? Are you going down or are you climbing? If you're in a boat in this river that makes this loop, right? Would you be going upstream or downstream when you go from E to D? You'll be going upstream, right? Because you're going opposite to the flow of the river. So that means you're going to higher ground. So the difference in potential then between going from E to D is going to be a positive number. So instead of being minus I times R2, it's going to be the current I times R2. Not with minus but with plus, because you're going up. Right? As I said, most of the time you would want to go with the direction of the current, but sometimes that is not possible. And sometimes you might forget that prescription and then you start going in the opposite direction and you'll be all confused about it and maybe use plus or minus where you shouldn't. So that's why we're doing this the opposite way. So when you go from E to D, you go up in potential and the magnitude should be I times R2. When you go from D to C, what happens again to the change in potential? Again, you must be going up. Imagine the resistors are waterfalls. So now you're going up on that waterfall. So you're going to higher ground. And this is how much you increase your height. When you go from C to B, nothing happens. Difference in potential 0. But now when you go from B to A, what happens to your potential? Which one is at a higher level? Point B or point A? Well, point B is connected to the positive side of the battery, so that must have a higher potential than the negative side of the battery, which is connected to A. So B is at a higher ground than A. So when you move from B to A, you're going downhill. You lost potential. So that's going to have a minus sign, and we know how much it drops. Epsilon. Right? So this is what, and since you're back to the original point, that's going to have to be 0. The sum of those terms is going to have to be 0. Okay? So compare the two equations. They're identical except that you multiply by minus sign the equation. So your answers obviously are going to be the same. Now let's think about the question of replacing those two resistors with one resistor that will do the same job. What does it mean to do the same job? The job of these resistors in this circuit are to control the amount of current in the circuit. If you have your battery with an epsilon for the EMF, and you want a specific amount of current flowing in the circuit, then you put your resistors that would do that job to allow a specific current to flow in your circuit. So when I say replace those two resistors, replace R1 and R2 with one resistor that would do the same job, what I mean is that, well, let's call that one R equivalent. What I mean is that when I get rid of those two resistors and I connect my equivalent resistor, the current in the circuit should be the same as it was before. So what kind of resistors would do that? Would do that job? So if you look at the equation that we have, the equation says that epsilon should be equal to I factor R1 plus R2 for the circuit where you have the two resistors in series, one after the other. No cables connected in between. Now the circuit that would have only one resistor will look simply like this, and that has an R equivalent instead of two resistors, right? So for that circuit, assuming that you have the same battery, what would be the current in that circuit with only one resistor? Well, the current in that resistor and the EMF of the battery would satisfy this equation. So if I want these two circuits to be equivalent, that is to have the same current for the same EMF, then clearly this number is going to have to be equal to this number. The equivalent resistance that I'm going to use, it's going to have to be the sum of the two resistors, right? So in a series circuit, as you can see, the equivalent resistance, let me put that. Right, that's what we just derived. It's important to be clear about the definition of series, because in some circuits it will not be so obvious that two things are in series. So what we mean by in series is that two elements of a circuit are in series if the current that goes through one of those elements has to go through the other one. All of the current that goes through A, if it has to go through B also because there is no other paths that it can follow, those two elements are in series. So the typical situation, of course, is your resistor, one resistor is connected right after the other. But there's other possibilities actually, because you don't have to have them right after each other for that to be true. Because the condition is that if the current that goes through one has to go through the other one, then they're in series. So this also is a possibility. You might have some resistor here, and then there is stuff in between them, C and D, but then RB is back here, right? So whatever current you have flowing through A will have to also go through B. Even though they're not right next to each other, A and B, you can still consider them in series because of the condition about the current. Has to be the same. If it goes through A, it has to go through B. Okay? So in that case, you can simplify this circuit by taking RA plus RB. If you want, you can remove RB and just put RA plus RB in place of RA. So RA in this example and RB are in series.